shells, some of them are live shells. But in the tropical oceans, warm oceans, you have these calcareous phytoplanktoners. And they are highly photosynthetic. They release a ton of oxygen, take in a lot of carbon dioxide. But there's one thing about these little critters, is that they dissolve very quickly. Chalk. You see the glass-like structure, diatom? Which one is heavier? What do you think is heavier? The chalk-like looking one or the glass-like looking one? Glass. Makes sense, right? Which one would dissolve quicker? The chalk-like looking one or the glass-like looking one? Chalk. Okay, so far so good, right? You don't need to be a scientist to know that. Or a policymaker, right? Good. So, a lot of these planktoners have rained down at the bottom of the ocean floor. They dissolve. And here's an image of the White Cliffs of Dover. And, you know, these are, if you take a microscopic cross-section of some of these cliffs, you can see fossil evidence of diatoms and phytoplanktons. But these cliffs were made from the raining down of phytoplankton over millions of years, and then uplift and plate tectonics has pushed them up to the surface and above sea level. And basically, we can get into a whole geology talk here, but basically this is part of the marine food web. And this is just another electron micrograph of a coccolithophore, Emily, floating around, absorbing CO2 and sunlight, and making sugar, and just growing and raining down and depositing on the bottom of the ocean floor. I'll keep it simple. Carbon, you got this carbon gas here coming out of the atmosphere, goes into the ocean as CO2, mixes with water, and it forms a strong acid. Okay? Immediately, Tums for the tummy, Pepto-Bismol comes to the rescue. Calcium carbonate, bicarbonate, buffers that strong acid. Where is that Tums for the tummy coming from? The dissolved little phytoplanktoner, that little Emiliana huxley, that calcareous shell. It dissolves and makes Tums for the tummy. So Tums for the tummy comes to the rescue, neutralizes this strong acid, turns it into a weak acid. And that's what you want. Why do you want that? Because the body chemistry of that little tiny phytoplanktoner binds and combines with carbonate with calcium, and you make calcium carbonate. You make a shell. So just like you drink milk and you eat sugar, you make bone. Drink milk with calcium. Certain plants have calcium in it. Goes into your stomach, goes into your blood. You have enzymes that take that calcium and the sugar, and you make bone. Well, the phytoplanktoner has a protein and an enzyme that takes carbonate, calcium, to make its shell right out of the seawater. And without the nice little greenhouse gas going in there, sucking it up, it wouldn't have its shell, and it wouldn't combine with it wouldn't combine with light to make sugar as well. So that inorganic carbon is used for sugars and for making skeleton. So let me get to a more simpler one. I like this one because it shows you that upper level, and you got all these guys here. You got little ones with arms and feet right here, a zooplankton. He doesn't stare in the light. He doesn't have that amazing ability to stick his head out in the sun and make sugar. He has to get his nutrition by eating a phytoplankton. So these things with arms and legs and little tiny antennae and eyes, those are heterotrophs. They eat the autotrophs. It's a little food chain. So I try to explain this to people that are making decisions on climate, and I give this talk all the time. I'm like, okay, wait guys, let's stop right here. I need you to get this. You got this calcareous critter on the top, and you got this other little critter that eats him. Right there is the basis of the food chain. It eating the other thing, swallowing it, digesting it, and releasing a fecal pellet, pooping, is taking carbon out of the atmosphere and burying it. So if the first step of controlling the greenhouse effect is the life cycle of a little phytoplanktoner and this little guy eating him, remember, the first guy, what's he doing? Sucking CO2 out to make skeleton. He's an important player in this whole budget. Really important player. If he doesn't get eaten, we wouldn't be this stuff down. Because if he wouldn't eat him and he would dissolve and just sit up there, what would happen with all that carbon? It would off-gas and go back out into the ocean. I'll keep talking about it. Just more awesome pictures. This is a picture of, they call it a whiteout, and in the Bahamas, this whiteout here is just excess dissolving phytoplanktons. Look at that stuff. So when stuff is not eating them, and remember, it doesn't just stop there. It doesn't just stop there. This guy is eating this guy, and there's another guy eating that guy. And then a bigger guy eating that guy. So you have this chain of eating and pooping that's taking CO2 out of the atmosphere right in the upper layer. And what probably, the tropical oceans are not good sinks for CO2. Not a great place for sinks for CO2. Why? Because those critters dissolve too fast. And they off-gas CO2. If they're not going to be eaten, and they're not going to be taken to the bottom, they don't do us any good. Well, I shouldn't say that. They do a lot of good. But they need to grow, they need to get eaten, and they need to be pooped out, or they need to die and float down at the bottom of the ocean. We don't like it when they're dissolving up here. Bad, bad scenario. And that, what happens is that photosynthesis exceeds respiration. Respiration exceeds photosynthesis. It means that there's a lot of off-gassing of CO2 and not a lot of photosynthesis where oxygen is produced and CO2 is being buried. Just some more pictures of these beautiful critters. Now, here we're getting to the diatoms. There's a planktoner. Looks like a little nautilus. But you start to see these heavier glass-like structures. Now, tropical oceans, you see more predominant these guys. In tropical oceans, warm. So, what's important about tropical oceans is that they're the basis of the food chain for plankton to grow. So yes, they're productive with fisheries. Fish are eating them, but they're not great at burying. The glass-looking structures, they're heavy sinkers. These guys eat the glass-like structure-looking ones and the chalk-like structure-looking ones. And these are called euphausids, zooplankton. This is like a humpback whale's breakfast. They are krill-like looking critters that are eating and grazing on phytoplankton. Right now, March 1st, as soon as you could just see the difference. The sun, it's 5 o'clock, the sun is still out, and right away my brain, since I have a marine science background and I've been reading about this stuff and studying it all my life, I just think of the Southern Ocean right now where the whales are coming up. The angle of the light is changing, the phytoplankton are coming up, the nitrogen and phosphorus is being upwelled, and there's a bloom, there's a big burst of energy in the global oceans right now where all the whales and all the fisheries are eating because of that nutrients that are coming from the bottom of the ocean and getting their way on the top of the ocean, and all these little planktoners and zooplanktoners are out there eating and grazing, and then the biggies come, the tuna, the jacks, the mahi, the sharks, the dolphins. It's like one big supermarket for a wide variety of fish in March. So March is the highly productive time because of the angle of sun. And again, these guys are eating the smaller guys. But getting back to the diatoms, the glass-like looking ones, they're heavy sinkers, and they're predominantly in the colder ocean. So diatoms are more predominant in the upper latitudes, not in the tropics. They're there, but not as abundant. So there's only two or three places in the world where these diatoms thrive, and the water needs to be really cold the water needs to be really cold for them to thrive in, and I'll explain it in a minute. These are just more pictures of zooplankton that eat those tiny little critters. More pictures of zooplankton. And then you got the biggies, because the little zooplankton attract small fish. And then these guys come. So you have this whole food, you have this whole trophic level, this whole food web of life that's occurring. And then the biggies. Now remember, very important to note that fisheries, like I remember, my professor back in graduate school knew that I was studying stuff that you can't see under the microscope, and he gave me a final project. Okay, your project is going to be